Okay, so this week's topic is mass defect binding energy per nucleon, and this is the reason how stars die. This topic is actually there. I'm in India, so in our class 12, in our high school, last class of high school, this topic is there. And the one thing I hate about teaching this topic is nobody mentions this is why stars die. Come on, that one sentence will make this thing whole lot more interesting than normally just try teaching it ever will. So let's get started. Kind of, I don't know what I'm doing today. I don't even have any notes around me. So yeah. Oh wait, I made one. Sorry. Okay, so the thing is that mass energy. You all have, I think everyone, yeah, almost nobody in this world has not heard of this equation. E equals mc squared. And today we are gonna use this equation basically. So what is binding energy or mass defect? Well, first let's talk about mass defect and binding energy. They are basically almost the same. Mass defect into speed of light square is the binding energy. So technically they are kind of the same, like the similar concept. So this is actually mostly studied in nuclear physics, like how the different nucleons, the proton neutron, are actually held together in the nucleus. This is mainly that concept, but this concept can be summarized into almost anything, like even in an sun and earth, this is sun, this is earth system, there is an whenever there is a bound system, there is a negative energy associated with it. And as far as this equation, whenever there is an energy that can be equivalent to some mass, so that means if sun and earth were weighed together, weighed differently from each other's influence, the total weight would be more than the summation of weight when earth is actually in orbit of the sun. But the thing is that in case of these astronomical things, this energy is tiny, so the mass will be literally in, I don't know, I have not done the calculation, but nanogram, microgram, I don't know, because gravitational force is not that strong. So yeah, that mass will be a negligible, highly negligible fraction of that total mass of sun and earth system or any system. You can think of it kind of like two magnets. If I take two magnets, this is north, this is south, this is south, this is north, and they are sticking together, so they are in a low energy system, like they are binding together. So technically, theoretically, if you weigh them and then separate them and then weigh them, those two masses are going to be different, because when this is like this, some of the energy is released in mc square, and that energy is a defect in mass, tiny bit, but it's there. Like binding energy is there, and it can be equivalent, means it can be equated in equal to mc square, but only thing where it is most significant is in the nucleus. So in the nucleus, let's talk about the nucleus. Nucleus, there is neutron, which basically does nothing. Sorry, I need to change my job. Yeah, and there is proton. This is no charge. This is positively charged. Now, in the nucleus, there are many proton and many neutrons. So mostly, like hydrogen only has one proton, so that's a different case. But these protons repel each other, so electromagnetically, electrostatically, or magnetic, they are the same force. Okay, So they repel each other, so they are held together by the strong nuclear force, and the strong nuclear force is so strong that they actually have a defect in mass which is converted into energy that we can see. So whenever actually in any element, if we try to find like okay, now one basic thing is that one atomic mass unit into c square is 931.5 mega electron volt. MeV, M is capital most probably. So this is a very easy equation, so that whenever in any case we need to find the what is the binding energy, so we can find it. So the mass defect or del M will be let's say the atom is XZA. So the mass will be, first this is the number of protons, so Z into number mass of proton plus how many number Z into mass of proton plus A minus Z, that's the number of neutron, into mass of neutron minus the mass of X is Z, this is Z plus. Actually there is no consideration of electron here, so we do not take consideration of electron here. If it's given like this, you can actually add electron, this will become Z into MP plus mass of electron plus rest are same A minus Z into M, and this is getting messy, but and then this will be whole M of mass Z A. This is the equation, this is del M, and normally whenever you have to evaluate it, these values are simply given in atomic mass unit, so you do not need to do the actual calculation of multiplying by c square, but whenever 1 AMU is 931, 1 AMU into c square is 931.5 mega electron volts, so whatever is the mass energy, you can find the binding energy corresponding to that is equal to del mc square, or like you can just unitary method, 1 AMU is 931.5, so whatever the del m is, what is its energy, so there that is. Now the point, how is this related to the stars dying? So there is an shed, okay, there is a graph, why did I give it a, sorry, this one, yeah. Here is a graph, I will put the photo up there. So this is the binding energy per nucleon. Now hydrogen has only one proton, but uranium has how many, 237, around 237, 235, there are many isotopes, but it has that many electron proton and neutron in its nucleus total. So 1 2 3 1 to this. So if we see the total binding energy, this is not a good measure, so we see the binding energy per nucleon, like how much nucleon. So the binding energy of the atom of the nucleus divided by the number of nucleon is the binding energy per nucleon. And if you see the graph, you will see hydrogen is way down, so whenever two hydrogen are fused, it gives binding energy, and whenever binding energy is reduced, it actually gives it is more stable. Like let's consider these three small nucleuses, so whenever they are binding together in some form, so what happens is some of the mass is converted into energy, so this goes out and this is the new nucleus. Let's say that was helium or something, and it became now lithium or something. So that thing is that if you wanna go from lithium, from this one to again to back three different things, you will have to give in this amount of energy from yourself, because it was released during this joining, so you will have to give back this energy. So basically this is more stable than the three equivalent forms, since it gives out energy and nature loves stability. So if you see the graph, and there is another thing, if you see the graph, it tends to be simply same. It tends to be simply same around from Fe is the highest binding energy. So basically, once you reach Fe, let's say this Fe, so if you try to join in another nucleon, or if you try to extract another nucleon, you will always have to give some energy. You will never get any binding energy out of it. So this is the most stable, and this Fe is the actual reason why stars die. And you will see this line does get down towards uranium, but it does not go down so much. So this can be explained like the strong nuclear force is a small range force. So whenever the nucleus is very big, the actual force is from one particle is immediate neighbor. Its immediate nucleons are affected by strong nucleus. So whenever the nucleus is getting larger, the electrostatic repulsion force makes it like less stable. So it goes less stable. Let's say this is uranium, and uranium or any heavy nucleus, and whenever it splits into two, some of that mass also gets as energy, binding energy. So whenever you have to fuse them together, you have to give this mass, so these two are more stable. So whenever everything comes to iron, this is the most stable thing, so nothing can be done about it. So how does a star work? A star is basically equilibrium system. Star is a very massive thing. So there is the whole star, and there is the nucleus. Let's say, okay, different color. This is the nucleus. So the stars are mainly made up of hydrogen and helium. So in the core, there the sun's enormous gravity is pushing it inward. So this push inward increases the temperature inside and increases the temperature and pressure inside. So the helium's nucleus start to fuse to form hydrogen, nucleus start to fuse to form helium. And when the core's hydrogen reserve is gone, that time it is not giving. See, the thing is that from hydrogen to helium, it's a massive increase. So that much energy is not given off, so the star starts to contract. So let's see, the stars become smaller, so the mass is the same, but the star contracted a bit, so the temperature goes up, and inside this core, inside a smaller radius, helium starts to fuse to carbon. And then when that helium is also gone, then starts contract a bit more, and that carbon is converted into oxygen, and the oxygen is converted blah 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 back to the core. Of the core is iron, and when it is iron, you cannot push in anything. Like up to this point, whenever there was any, wait a minute, yeah, this is a line from a book. Energy generated by a fusion keeps the center hot, and the thermal pressure of this hot gas of this fusion, this binding energy that was releasing, keeps gravity from collapsing the star under its own weight. Whenever Fe is formed, there is no more kinetic energy that's given off in binding energy of the fusion product. So the star implodes inside, like the core implodes, and the core, whenever the core implodes, it releases enough kinetic energy for the star, the onion of different elements except the core, everything gets shoots off in a supernova, and the core becomes a neutron stars, and we get all these elements. All the elements in our periodic table are mostly made up by this process. There are more violent supernovas, there are less violent stars. This is the moderate range for which there is neutron stars are born. For low range like sun, it will form a white dwarf and it will not go supernova like in this case. And for some very massive stars, it becomes a black hole in the center and goes supernova. So basically, Fe is the thing that is making all this supernova. Now, Actually, most of this is from this book, and this is an amazing book. There is the graph is here actually better. Like this graph, that one is mostly, the previous one is mostly what you will see, but this is, I think, better because it shows you an analogy with something else, like a ball rolling from hill. Let's say hydrogen is the first ball. So whenever you see, the ball will try to get lower, 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 and whenever a ball is falling from a height or a potential, it gains some kinetic energy and releases this energy kind of, so it becomes more stable. So the ball always flows downhill, we know that. So it's like it's flowing downhill, 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 iron. And now whenever it goes anywhere, it's always a up, so you will have to give energy. So iron is the most stable. And here you have uranium, same case, this goes down, 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 down. So iron is the most stable element, iron 56 to be precise. Iron Fe56, sorry, 56. This is the most stable of any element. So this is how things are mostly going in the universe, and this is why we exist. Because if iron wasn't the most stable element, then the star wouldn't probably implode, and the supernova wouldn't happen, and the elements would not be there, and we will not be here, because we ourselves are the remnants of the fallen stars. We are stardust. That's from Carl Sagan. He's the best. So if you can, this book is quite costly, like 1000 rupees, this one book. But if you can buy it, buy it. It's an amazing book, so you will love it. I think that's it. 16 minutes. Most probably I said everything I wanted to say. Not in the most efficient way, but I did. Let's see. With time and time, I will become more efficient. Thank you.